So I'm going to talk. I guess the closest thing for this topic is domain-specific languages for epidemic modeling, but it's only kind of sort of that. Really, I'll be talking about two modeling frameworks. One that is existent, flepiMop, and one that is in its infancy, which is tabularepimdl. And talk a lot. I think that the interesting parts of this is I'm thinking about the other in the context of one. So flepiMop is also the modeling framework formerly known as the COVID scenario modeling pipeline. This was developed to provide modeling support, starting with scenario modeling and moving to forecasting in response to the COVID-19 pandemic. So, I mean, what really happened is we had a model that could be used for some scenario modeling that we needed to deploy something quickly for California. We did so. And then more and more people were asking us for help, and more and more people were people were wanting more and more capabilities and things beyond scenario modeling, including inference and stuff like that. And everything grew and grew and grew and grew and grew and grew to make it complicated. So this pipeline had no intention of ever being a domain-specific language for modeling, but it kind of, in the end, we developed one, largely driven by Joseph and Allison and Josh to do it. So just to give you a sense of what flepiMop is, it's a it's a modeling pipeline that can can take advantage of pretty complex compartmental models. It can do it on a transmission network like the United States, here shown with interconnectivity by states, though originally, excuse me, originally we were actually doing this at the county level with county level networks, and it's a meta population model, nothing exciting, but we do have a domain-specific language, or effectively a domain-specific language in the form of a configuration file that allows us to set up a very complex model very quickly. So this consists of a global header that gives us information, all sorts of general information, including a lot of information on how that's sort of slowly being deprecated out on how to run on AWS and fast systems because, for a brief moment in time, we evidently had infinite AWS resources, of course, according to Amazon at least. But we got close to testing it, but never quite did. But then it also has a spatial setup that, and all of these have, reasons behind them of problems we were trying to solve, So it had to take account of the competing resources at our disposal. We needed to be able to implement the models quickly at different spatial resolutions and for different geographic and different locations. So, we have a spatial setup that can basically take in the information on any location at any resolution. So providing we have, transportation and mixing data and the like. And it's generally flexible to any population structure and mobility matrix. We're going to come back to this because this is where I think it starts to get into the idea of being a domain-specific language, in that we have this idea of compartments and SEIR model definitions that define the compartments of the underlying model and transitions. It has composable compartment types and a flexible approach to defining transitions, and also allows us to define different methods of simulation, whether quickly move between stochastic, Runge-Kutta, and other types. You need to have initial conditions, and nowadays we want to start from some sort of sample from some sort of relatively fixed level of initial conditions or fit for a long time, whereas early on, early scenarios, we had to be able to really try to understand the potential seeding conditions because it had a huge impact over the epidemic dynamics, particularly as surveillance was scaling up. Outcomes, we need like different compartments and different transitions can define different outcomes such as hospitalizations, deaths, case detections, and we allow those to be time varying based on changes in surveillance and severity, and also to have potentially complex distributions in their relationship to the event because there's delay distributions around observations. Critically, and from the beginning we had, this is the part of the language that actually existed from the very beginning, the ability to specify different interventions and very flexible structures of interventions over time and space and phenomena. And for historic reasons, this is the mechanism by which inference occurs. In the sense that you have a baseline distribution of a parameter, and then you infer some actual change on it in time. And then finally we have inference, so we have to be able to flexibly specify multiple outcomes and different levels of spatial aggregation on which to do inference on, and inferences have to be parameter and intervention specific, and we have prior. So let's just go into a little bit of this as a domain-specific language. So flepiMop must support a variety of different model structures with few modifications, as I said. So, and we don't want to enumerate necessarily the 8,000 compartments that we might actually have to enumerate if we were going to. So we are able to specify and everything sort of in this quote unquote language is done in YAML files. But here we're able to specify okay, we want 3 affection stages, SIR, age groups, child and adult, vaccination status, vaccination and unvaccinated, and then we will automatically generate the composites of all of those different potential areas in terms of compartments. So we can quickly specify the various types of compartments we can. So then, of course, it's not enough to specify the compartments, to specify a compartmental model. We also need to specify the transitions and how we get between them. And, we've come up with a moderately flexible way to do that accomplishes, a fair number of our needs. And so this allows us to by specifying these transitions, and we don't have to specify if there's no specificity on a dimension, that part of the dimension, right? Like so for instance, if your S to I transmission doesn't really depend on your age, you don't need to necessarily specify that. But you specify the sources, and this is saying things come from S, and that can be S over unvaccinated or vaccinated. They move to I, where it is I is unvaccinated or vaccinated. This is proportional to the S vaccinated, S unvaccinated, those two pairs, and the I is sort of broken out so that, broken out, and then these rates down here specify that basically that we're in a composite over this beta that's shared, and the theta u and the theta v that go out to the others. And then we also allow an exponent. So this is not obviously comprehensive in all possible transmission functions. And this is, part of why I'm going to show you something else after, but it is reasonably flexible. We can also have modifiers that we have we also then can specify the parameters. They can be time varying. So for instance, we could have a seasonal modifier on our reproductive number. We can sample from a distribution. For instance, we can just sample randomly as to capture underlying uncertainty from the distribution for vaccination. And then we can also perform inference by specifying a overall distribution that the parameter, basically a prior distribution, some truncation, and a perturbation rule for an MCMC sampler, where we kind of have our own home-cooked thing that's like highly parallel, and tries to, basically what we do is we optimize states individually. We let states optimize themselves individually, or locations optimize themselves individually. And then when those individual optimizations, like going through and have an accept reject on each there, and whenever a global across, say, the entire country, realization beats the likelihood of a previous one, or fulfills the MCMC rule for the previous one, we go and we accept and reject. So this is something we built up over time, and it does provide us flexibility within this set of compartmental models, and you can read all about it, download it, play with it, do it at flepiMop.org. We made this during the pandemic. I think we did an okay job. I think we gave some very good information and advice to some folks. We gave some okay information and advice to others. But this was a good tool. This is not what I wish I had. This is not, even where it is now, which is very effective and can do a lot of stuff, it is not what I wish I had. And so I've been working on, sort of in between the cracks, like when my daughter's going to sleep, a framework that I wish I had, which is tabularepimdl. So first to say, right, this is not a domain-specific language per se, and I'm not even sure what I wanted was a domain-specific language. Instead, it's an object-oriented programming framework, but maybe it's a little bit of both. And why I wanted that, I have to reveal a secret to myself, is I wasn't always an epidemiologist. I used to be a proper software engineer at IBM. So I've been spending, to 20 years since I left software engineering, I've just spent my life pining for good object-oriented programming frameworks and not having them. So I'll talk a little bit about the tabular epi idea and the implementation and show you a little of the implementation as it is now, which is hopefully useful for thinking about conversation and stuff. I do want to have two disclaimers. That one, I'm not claiming anything here does anything new or unique. Basically all of the talks that we heard today, most of them, showed things that did part of, or maybe even all of what we accomplish or what I'm trying to accomplish in this particular framework. But I do think it does it in a way that would make these things in a way that would make practical tasks and modeling exercises easier over time. Another way to say it is I think this does it in a way that would have allowed us to, in a crisis, have more development discipline and development and software engineering discipline while we were doing what we were doing. And also developments and specifics in very preliminary stages, so things are very much in flux. So the basic idea is not in any way shocking or interesting, right? It's, okay, we have a tabular set, I don't know why it just says tabular set of the world, a tabular representation of the world. There's a set of columns that represent the world, and it's kind of represented in the sense that, we have a state, we have some series of state columns that say something about a state, your infectious state, your vaccination state, where you are. We have an indicator of time, and then we have the number of people. That doesn't have to be a whole number, though here I'm going to have it be a whole number, that fulfill, that meet that signature, right? So you can have a lot of potential signatures, but that don't exist because nobody meets them, which is one of the nice things, I think, compared to sometimes when you're making a very complex compartmental model where a lot of people may not exist in any of the states. You apply a set of rules. Whoops. Oh, this keeps freaking me out because it's showing me the next thing there. You apply a set of rules, and that'll give you a delta that updates that tabular state of the world into the future. Right? Nothing shocking here. Then the epidemic model is then becomes a set of rules. So we have, so we create rules, and every rule sort of has to have initialization. It's a class. It has to have some function that allows you to get deltas to get to the next state, and then it also has to be able to write itself to YAML. And then we can define an infection rule. Here's a simple infection rule, beta 0.5. The column that it operates on is infection state. And then we can also define a simple transition. For recovery, it's simple transition. It operates on infection state also. Because it's more general, we define the from and to, and there's a rate. And then the epi model just composites those two rules together, starts with a population, voila. We run and it does it. So, okay. So now let's go through what this helps, how this way of approaching things helps with things I wanted to do. So one of the things I wanted is the ability to add observation states. Right? So I wanted to be able to, without really thinking about my underlying epidemic model, add a ton of different kinds of observation states and put them in and take them out as I wanted without messing anything else. So I can do that. I define a rule around I've created rules around simple observation processes that have some rate, and I can so I can make my model be my infection process rules and my hospitalization rule, and I'll come up with something where I have people in hospitalization states at different times and different infection states. And, and I also wanted to be able to easily combine stochastic processes and deterministic processes easily and dynamically, changing back and forth between what processes were stochastic and deterministic as needed based on the problem and what inference. Like, for instance, the deterministic. So, and had composite. So, for instance, here, I've made this hospitalization rule stochastic, but these infection rules are deterministic. So I've quickly made a deterministic epidemic model that produces a stochastic realization of hospitalization histories. I wanted to be able to, and this is what really drove me to finally go here, I wanted to be able to easily deal with complex immune histories and strain competition. So I want to be able to make these models where I have different, instead of having to represent multiple immune histories and multiple combinations, I can have independent processes representing my history of infection with different strains as they came in, because I never knew, you never knew which one was coming in next. And then be able to define rules based on these signatures. Here I have a cross-immunity rule, based on a cross-immunity matrix where you sort of have your highest level of possible immunity. But you can think of other rules where it's the number of I's that are in this column, right? It's the number of I's in the column. It is or a number of R's rather, number of past infections in the column that dictate your immunity. It's the a waning function of different strains based on T. But I wanted to be able to create those, add those additional strains without having to rethink the whole model or create a whole set of complex compartments, and be able to define these immunity rules and ways of protection based on some analysis of this signature that was not having to specify all the different apartments, right? And that is probably the biggest thing. And this lets you do this very simply. Here in a kind of simple one, have a protection matrix, multi-strain infectious process. We specified that, our typical recoveries, and we can quickly simulate, here three strains competing, where this third one has this weird space where it's like because of its protection, or the second one has this weird space where because of its protection, and R it sort of sits on. I wanted the ability, and another one I wanted the ability to do is to model at different levels of the population resolution in single framework. I wanted to be able to make household models and make household models and compartmental metapopulation models and different models like that without flipping frameworks. And that's very easy to do in this, because we can make a rule about people who share or don't have share a straight trait, in this case household, and their infectivity, our same old transmission trait. We just define a population that looks like this, and lo and behold, we have a household transmission model, and we can compare that really quickly to our SIR model. We can run it, and we can do the fun things that we all know from our analysis. If you run it like deterministically, it looks kind of like the SIR model, but you get very big differences with household things that are stochastic processes. Fun, but we can do this very simply, and we can do it in the exact same framework with the exact same tools and the exact same classes, except where it matters in that transmission process that we're using for the to do our other modeling. And there were other things I wanted to do that this can do. One of them that was very important to me that I didn't talk about much here is track individual operational processes. Sometimes there are very important operational processes that have little to do with the infection process, but we want to track independently and track how they're interfacing with the infection process, and this ability to sort of divide up how we operate in the different columns, but still have them matter for the other columns is helpful for that. I wanted to be swiftly adaptable in terms of changing whether different traits impact the infectious process, in the sense that like I have a hospitalization process that I put in and run for a while without it changing the infectious process, but without changing any other part of the model, have that impact the process. Easily add and remove demographic processes, and I'm getting more and more comp sci-e and software engineering as we go down, create subclasses of processes and composite processes, that build on the work we already do. Really, I wanted a coherent object-oriented programming model with direct mapping and descriptive config files, and also wanted to be able to make, and this is probably in some ways the biggest thing, in some ways the least important thing, but make fundamental changes with minimal code impact and not creating model branches. As we added capabilities to flepiMop, our GitHub was a nightmare to see. A project managers just, would cry just from like briefly glancing at our branch and history, our branches. And that's because there wasn't this nice clean object framework where where things were compartmentalized and there weren't cross dependencies. And that, oh, my life would have been different. But yeah, okay. So all of this is some ideas. As I said, it's as much ideas as it is it's implemented, but it's not at the levels it needs to be a practical tool yet. And two big things are inference and how to optimize inference and performance on this that we're working on. But it does, I think, encapsulate my wish list to some extent. I have put people's picture over their names, but there are a ton of people and a ton of funders who've worked on this over the past 4 years, the flepiMop part of it, and there's a couple of us who've, been up in the middle of the night trying to make tabular epi. So that is that's my talk. Any questions?
Any quick questions for Justin before coffee? Yes, okay. Yes, I had a question which perhaps we'll talk about later on, but so you've got processes that occur within the columns of the table.
Mm-hmm. And they can potentially affect each other, but
they can potentially interact, right?
Yes,
okay,
yes.
fine. Right, that was my question. Right.
Yes,
that was easy.
well, that's part of the point is to have to have them be able to interact with like general rules that don't so we could have a rule like counting counting the number of times number of Munich speakers I have.
Sure. Yeah.
Right,
okay.
and have that affect all the processes in a uniform way, as opposed to having to fiddle out all of the different, transitions and how that would work. Not that there aren't other ways to do that, just to say. Aaron.
Yeah, really, thanks for the talk. It's very interesting. And I'm intrigued by the data structures that you found useful in terms of this model specification problem. And that this tabular form strikes me as really interesting and very powerful. Forgive me if I've misunderstood something, but it seems that you supplement that with some sort of code as well that implements the rules, that tells it what to do with that.
Right, the rules specify, what to do with it, yes.
How that tabular information is then converted into actual calculations. Have you given any thought to how you could sort of systematize the rules in a similar or maybe quite different script, sort of model specification language? Because the tabular thing is really powerful for specifying the model, but the rules are the other piece, right? And then that seems to probably have some simple structure as well.
Right, and I think there's a way to do it, and I think there are people in this room who could do it very intelligently. I'm not sure I'm that person, but I mean, it is set up now that all the rules, we can do basically a YAML representation for all the rules, but that's just, all that is a more efficient, or not more efficient, more human readable to some humans, not necessarily this one, but some humans version of the code, right? It's not of the model code. So it's not that, I don't know that that's particularly, particularly there. But, the rules, like there are classes of rules, right? Like simple, like there are transitions, right? And there are rules that specify transitions. And you could see tying those to a more efficient representation that could be written out in more of a, like Odin dust type of way or whatever. Yes.
Okay, I'm just wondering if you can describe how that tabular structure is different from a definition of different compartments, one per row and being the column.
I mean, it is like, it's very similar, I forget who was getting to talk to me, but you know, how the agent states were being defined, where you had like sort of the parallel different, you know, the parallel different states, right? And the parallel different processes for different state, you know, different attributes of the agent. So it's very similar. I'm not saying it is fundamentally different than that, but I think it's the idea is that by setting it up this way, it's easy to make those processes by which things move between states dependent on the other columns in ways that are very general. So another way to say it is like if I kind of write out the complete compartmental model, parallel compartments, right? I sort of need to sort of add, you know, expand the number of compartments as I get possible attributes in, well, okay.
Let's say you had like 16 age groups in the model. Would that multiply the number of rows we have by 16?
Mm-hmm.
In your table? I'm just wondering whether I've got the structure.
If you, it would multiply that. If you had 16 age groups, it would multiply it by 16 if there were extant states for everything, right?
All right, so you can get rid of the ones that
Yeah. So zeros don't exist, right? So there are a lot of implied possible compartments. You know, they're implied possible row states that don't exist. So if they don't exist, they don't, right? So the initial state is usually just, you know, for a simple SIR is just 2 rows, all the S's and one to represent like the one I person. Yeah.
I think that.
Well, so this is, I guess, digging a fair bit into the performance thing. So you're saying, in some sense, there's like a potentially sparse tensor representation implied by this tabular zeros aren't represented, et cetera, But
Yeah.
for performance reasons, you would probably, or in many cases, you would want a full non-sparse tensor to then just do the like staged operations on if I'm feeding this into a GPU or TPU, right?
Maybe. I would have to think about that. But yeah, maybe. There might be ways to optimize. I mean, one thing I'd say is, right, so it is representationally, you're going for representational simplicity, right? You're going for the fact that, right, when you, right, like I did a calculation around Omicron about the number of immune histories that people could have, not even taking about the time of events, but just whether you were infected with, you know, alpha, delta, you know, wild type alpha, delta, had vaccine, you know, series 1, dose 1 of your first series, dose 2 of your series, your...
Manufacturer of vaccine.
Right, yeah, even leaving aside those types of things, right? You quickly got into the 2000s, so.
Yeah.
Right? And I think there's value in both bringing in data and stuff like that to be able to represent all of those individual histories, but all of those, but there should be a way to summarize the immune impact of, but we may have a simpler way of summarizing the immune impact of those histories in a nice, concise composite rule. And I think the power of this representation to me, and to the way I think of things, is that ability, right? Another example where I think this becomes useful is so, like when you do operational modeling, this gets to this operational representation idea, like you do modeling of measles, right? From, you know, because of the ways measles immunity works, right? From an immunity standpoint, you are that, you're immune or you're not. And the model only needs to know basically, do you have maternal immunity that's going to fade, or do you have vaccine or natural immunity that's never going to fade, or are you infectious or exposed or susceptible, right? Like those are all the things the model needs to know. Operationally, people who want to do simulations of their impact of of like doing another vaccination campaign on top of their 2 doses that they have from their routine vaccination program and the vaccination campaign they had 2 years ago, they care a lot about when that immunity came, right? And it's really good if you can track that and pair that to people's immune states. But it has 0 effect on your disease model, right? So it's good to have a simple, conceptually simple way, or at least for my brain, a conceptually simple way, to divide out those 2 processes and be able to keep all that information about the, those processes, not to mention demographic and aging processes and stuff like that, without being burdened, or without that burdening the complexity of how we represent the disease process itself, right? So it's that, that's one of, so those are the 2, and those are the 2 sort of things, like the 2 use cases that like sort of sent me in this direction. Yeah, for what it's worth.